Okay, so let's take a look. Absolute value functions, last topic of chapter 2. This is something that, let me get all phones and stuff away, please. Everything, all that stuff away. Okay, so this is something that that you're familiar with. You obviously know what absolute value functions are. You know how to take absolute value, how to evaluate absolute value functions. But we're going to look primarily at what the graphs of absolute value functions look like. This is a really important section. Hunter, why don't you put that away? Take a look up here real quick. You guys will have time to look at that stuff. This is a really important section because it illustrates the way that we graph functions in general, where we can come up with what we might end up calling a vertex form. Things like an absolute value function are going to be very similar to, in coming chapters, parabolas, because they have a vertex, and the coordinates of the vertex are defined, and then we're able to make a quick sketch of the function based on any function multiplier and the coordinates of the vertex. Now that's a lot of words. You might be thinking, what's he talking about? That's why, just giving you a little heads up, that's why this is so important, because the way that we deal with functions with absolute values, which are pretty easy functions, is going to be consistent throughout the year. So first of all, just a real quick review of what an absolute value function is. An absolute value function is best defined as a piecewise function. That's that stuff we talked about on Friday, right? And I know you haven't had a chance to really do much with this, and I understand that. So here's kind of the plan. Once again, we'll take a quick look at this. I'm going to put an assignment up, which will be up, I don't know, it won't be up probably until after school at the earliest over absolute value. But I'm assuming people haven't finished up the piecewise function ones yet, right? I mean, you still need some time on that. That's fine. We'll test tomorrow. Yes, sir.
When did you put in the piecewise function?
I put the assignment up on Friday. Did it not show up there?
I didn't see it.
Okay. You didn't see it on there?
Is it in a different section?
No, it should be under Unit 1.
I didn't see it.
Okay, so maybe I forgot to turn that on for you guys too. I'll turn that on. No, it's really no big deal because I was assuming you guys would be kind of preparing for the test anyway. So I'll turn that on today. The test will be tomorrow. The test, though, remember, this really is kind of old stuff. It's not a big deal. We'll do the test tomorrow, get that out of the way. Wednesday, I'll give you a full lab day to kind of work on this stuff and get questions answered. Piecewise functions and or absolute value stuff. Okay, make sense? Okay, so an absolute value function is best defined as a piecewise function. We can define it if the argument of the absolute value function, remember what that means in math. The argument is just everything that we're putting into the function. If the argument is positive, for example, absolute value of 7, what does the absolute value function do? What's the absolute value of 7? 7. Doesn't do anything, right? So if x is positive, in this case, then the output of the function is just plain old x. The absolute value bars didn't change it at all. Make sense? Okay, but if the input is negative, so in the case where the values of x that we're inputting are negative, what do we do? Well, what's the absolute value of negative 7? 7. Now, how do you turn a negative into a positive? Well, I mean, but what do you multiply by negative 1, right? We multiply a negative by a negative to make it positive. And so in the event that the input is negative, we're going to multiply x by negative 1 to make it positive. And then the in-between case would be, what if x is actually 0? Well, what's the absolute value of 0? 0. Okay. So that's how we define an absolute value function, right? And we'll talk more about that. You know what I might do real quick for you guys, just because with this class, you guys are so advanced. I want to maybe just real quickly, let's look at, while we're on that subject, let's look at one case where the absolute value function, where it's not just an x in there. Say it's something else. Say we did something like absolute value of x minus h. And we'll even go further than that later. What's our piecewise function going to look like now? So the argument is the x minus h, right? As long as the quantity x minus h is positive, it's not going to do anything, right? Agreed? So how do we say that then? That's the part that goes over here. That's the domain part. How do we say x minus h is positive? Well, we could start off maybe just by saying that. X minus h is greater than 0, right? If that's true, then we don't do anything. We just leave everything in the absolute values alone. So the absolute value of x minus h in that case would just be x minus h. But what if x minus h is negative? What do we have to do then? We got to multiply everything that we input by -1. So we get minus the quantity x minus h, right? And then in the event that we get this in-between case, where x minus h actually equals 0, then we're putting 0 into our absolute value function. And what do we get back? 0. Okay? So that's just a little bit awkward, though. That's the way we would define this as a piecewise function, but here's where this is just a little bit awkward. We want to have our domains defined in terms of x's, right? We'd like to be able to say, for x is greater than some number, or x is less than some number, right? So we want to know, does that make sense? We want to know, where is this thing going to transition? So what do we have to do to each of these domains over here? If I want to write them, instead of writing them this way, I would prefer to write them as something like maybe, up here, I prefer to write it as x is related to some value. So what do I do to solve for x there? Add h, right, to both sides. So isn't x minus h greater than 0 when x is greater than h? See what I'm saying? Everybody see that? Okay, and isn't x minus h less than 0 when x is less than h, if I just add h to both sides? Right, so you see how this is consistent with everything you've done in the past. By solving for h algebraically, what you've done is you've written these domains in terms of h, so they're useful. So now we know where on the graph is the absolute value function going to produce that line, right? In terms of h, and h could be anything. When is the absolute value function going to output that line, which is different? Well, there. And where is it going to have a value of 0? When x equals h. The in-between case. Okay, make sense? We'll come back to that. We'll come back to that again. But that's a good introduction. Okay, so we know then that the graph of an absolute value function, if we think about what we just graphed, right, if we go back one slide here, this absolute, if we write this as a piecewise function, really the absolute value function is just two separate lines, right? We either get y equals x, which is pretty boring. Y equals x is just a line with a slope of 1, y-intercept of 0. Y equals negative x is a line with a slope of -1, y-intercept of 0. And so isn't that it? Right? If we graph these as piecewise functions, didn't we really just, here's our breaking point. Whoops. Oh, what am I doing? Here's our breaking point in the middle, like we talked about on Friday, right? Everything to the left is going to be the graph of that left function, where x is less than 0. Everything to the right is the graph of the right function, where x is greater than 0. And they meet at the point 0, 0 in this case, right? So it's really just a graph of that piecewise function, like we talked about on Friday. Okay, there's the line y equals negative x. There's the line y equals x, right? And they break at x equals 0 in this case. Notice that this is characteristic of these piecewise functions. They're shaped like a V. They have this is really important, they have this folding symmetry about their midline, which we call the axis of symmetry. And all that's ever going to be is just a vertical line through the vertex. And that's the vertex right there, the point. Okay? So then if we move to something like this, now the vertex this time, we're going to get a little more complicated. Instead of just limiting ourselves to the absolute value of x, let's expand this to be y equals, this is going to be our new standard form.
Over your line.
For an absolute value function. Or actually, we probably should call it our vertex form, but it's the parent graph, right? So, or it's how we're going to tweak the parent graph to make a new graph. The parent graph was just that simple little absolute value of x, that v function. Well, we can take that plain old v function that we started with, and we can make any conceivable absolute value function out of it by just dialing in these three parameters, a, h, and k. Now, what do they mean? H and k are just going to be the coordinates of the vertex of our absolute value function. So wherever we want the v to be, it's going to have the coordinates hk. And a is the multiplier, right? It's the scale factor for the function. But the way to think about a, I'll give you a good way to do this. It's a little different than what the book says. They tell us that when a is less than 0, the graph opens down. When a is greater than 0, the graph opens up. But here's the best way to think about it. A is equal to the slope of the right-hand leg of the absolute value function. And the left-hand leg is just going to be a mirror image of that. Okay? So let's look at an example. Okay, we know that if a is a big number, a is going to be stretched out, tall and narrow. If a is a small number, if the absolute value is less than 1, it's going to be squashed, like we looked at the other day. Okay, but think of the slope of the right-hand side of the vertex. So to graph this thing, it's really simple, very simple. All we do is we plot the vertex. That's the point of the v, right? That's our first step on the xy plane. Next step would be we'd use a slope triangle to determine, to find another point on the right-hand leg. Okay? Then we'll, connect or extend. Then we just reflect over to get the left-hand side. So let's do an example. Okay? So what about this? Okay, now what we want to do here is we want to compare this to the vertex form of an absolute value function. Remember what that was? Our vertex form was just y equals a times the absolute value of x minus h plus k. So if I can just determine what the values of a and h and k are, it's really simple to graph this thing. Right? That's all there is to it. So let's just write those down. What's a? -1. What's h? -2. Good. Good. That's the part that's a little tricky. Remember, like, same thing, same way it's going to be with parabolas, same way it's going to be with polynomials later in the year. The vertex is always going to be located, the x-coordinate of the vertex is always what is being subtracted from x in the function. That's the part that trips people up. Everything else is pretty straightforward. But in order to get a value of +2, then I must be subtracting -2. These two signs are always going to differ, right? I mean, it's always going to be the opposite of this sign right here, the value of h. It's going to have the opposite sign of the operation between x and the number, if that makes sense. Questions?
So even if it's negative, it's going to be positive?
Yep. Exactly. If it's positive, it's going to be negative. Because h is the number that's being subtracted from x, not added, right? So h is -2. What's k? Now, k is simple. K is just 3. So what that's telling us then is the vertex has coordinates -2, +3, right? And so if that's where I'm going to put the point of the v, and then I'm just going to use this a in a slope triangle to extend the right-hand leg of the v. So let's watch that. So we found our values, right? There's our the vertex we said has coordinates -2, 3. So there it is, -2, +3, right? And now if I want to graph the right-hand side, you told me that a was -1, right? So I'm just going to go down 1, that's That's my rise. My run is +1. And there's going to be my second dot, right? And so I just connect and extend, and there's the right-hand leg of my V. Okay, what do I do with the left-hand leg? I just reflect it over my axis of symmetry, which remember is just a vertical line through the vertex. So if I reflect it over, isn't the cousin point of this one going to be right there? So that's it. That's my absolute value function. Simple. Okay? So there's my point. Plot the other point on the other side. Connect and extend the right. The reflection of that's going to be the left. Yes, sir?
What's the +3?
The +3. Remember, that gave us a y-coordinate of 3 for the vertex. And so if you think about what this did in terms of our parent function, we could think about this in terms as a transformation also, couldn't we? Think about the stuff we're doing. What we've done for this transformation, if we work inside the absolute value bars, because they're grouping symbols, we started with, this is kind of interesting to do. And this is where, isn't it cool that finally in math you get a chance to kind of pull all this stuff together and it starts to really make sense. I mean, it all starts to be self-consistent. That's when it's the most interesting. So there's our parent function, right? There's y equals the absolute value of x. If we add 2 to x, doesn't that mean we're just taking this thing and sliding it over 2? Right? That's the first step. Then we follow order of operations. The next thing we would do outside of parentheses is exponents. There are none. Then we multiply by -1, so we reflect this over the x-axis, right? So now it looks like this instead, right? And that's gone, right? This is our new one. And then what's the last thing we do? Oops, I'm sorry, we scooted it over here too, didn't we? I messed it up. So we moved it over, then we flipped it. So at this point, we've got this, right? After we get to here, we've got a function now that looks like this. It's been scooted, -2, then flipped, and then the last step is to add 3, which just means we move it up 3 to our final position. Okay? But you don't have to think about it that way anymore, because now we can just compare it to our standard form. We can just identify what's h, what's k, there's our vertex, use a to generate the right-hand leg, reflect it to get the left leg, and that's a little easier, a little quicker, right? Questions? Okay, I didn't think so. Okay, this quickly. So what's this one going to be then? Where's our vertex going to be on this one? The vertex is going to be at hk, right? So what's h? 1, right, Cammy? Because we're subtracting this time. And, okay, 1, good, there's our vertex. What's the slope of the right-hand leg? -1, that's all we need, isn't it? And we're done. Right? Over 1, up 1, slope of -1, we're done. On this side, then we just reflect it over for the other side. Always has to make a V. Okay, now we'll do it backwards. Now we have to write the equation based on the absolute value function. So this is different. Now by inspecting the graph, we have to come up with the values of h and k and a, which we'll plug into the parent function to write the equation, right? So by inspection, what is h? 0. The x-coordinate of the vertex is 0, right? What's k? -3. And what's a? 2. +2. If I look at 2 convenient places there, I'm going to rise by 2 and run by 1 to get to my second point, right? So a is 2. And so then we just plug that into our standard form, or vertex form, I should say. Y equals a times the absolute value of x minus h plus k. That's a flashcard thing. Throw that on a flashcard. Just, accumulate flashcards as you go. If I plug all that stuff in, I just get 2 times the quantity x minus 0. What's x minus 0? X, right? Plus, or minus 3. vertex is at 0, -3. A is 2. So when I plug all that stuff in, that's my answer, right? I don't put the x minus 0. I simplify that to just plain old x. Okay, make sense? Okay, what about that one? What are the coordinates of the vertex? 0, +3 this time, right? Slope is 0.5, or is fraction 1/2, rise 1, run 2. So I'm just going to get then y equals a, which is 1/2 times absolute value of x minus 0, just x, plus 3 this time. Okay? Got it? We good?
Yeah.
All right, so when are we out of here? Maybe there's time for us to head down real quick. 11:20. Yeah, might as well.
Yeah.
Might as well go to the lab. Let's go ahead and go down to 205.